It should be sharing.
The sharing?
So I hit present to everyone.
Yeah. Okay. Welcome to time series analysis, SDLE time. So today, at the first part, I'm going to cover the time series analysis. And you have access to this presentation. It's already posted on SDLE repo 17 time. And so this presentation was actually generated by the Beamer presentation with R Markdown. So I'm going to go through just the R Markdown and regenerate all of these slides. So let's start with time series analysis. So first of all, just as a recall of what is time series. Time series is of a data points indexed. Any data points that is a sequence taken at a successive, equally or unequally spaced, we call it time series. But most of the cases we have, in the most common cases, we have the equally spaced time series. And so we have the sequence of discrete time data. So I'm going to use the LA pollution mortality study example in my presentation today and do all the analysis over this data set. So let's first of all look at the data set and see how does it look like. So these are all the packages I need for this to regenerate all of my plots and my analysis. There are many, many more packages if you just search for time series analysis in R, but I found these the most useful ones. So let's look at let's run this part first and look at the head of the top data set that we have. Okay, so you can see that the head of the table that we have, the table is actually shows the LA pollution for the 10 years. So if you look at the help of the lab, you can see that it's for 10 years of the data set for weekly data. So each year we have 52 observations. And these are the variables in this data set. So I'm going to focus on the cardiovascular mortality and particulates and temperature. So today I'm just going to focus on these variables for my analysis. So you can work on any other variables. So these variables are all time series variables. Let's first look at the plots, how to make the plots for the time series. So let's check the class of my data set. I wanted to run this control enter. Okay. So we can see that the type of the variable I have right now is numeric, but most of the time we should be careful that for the time series analysis, the type of the or class of the variable should be TS, not the numeric. So that's why if I plot this, you can see that if I just press the plot for this variable, I have the plot with dot points, which is not the common type of the plots for the time series. So for the time series, we usually prefer to have the line of the connect the observations or data set with the lines. So this is the most typical type of the plot we have for the time series. So we can see that the only difference between these two commands is just type L. But instead of doing that, I can define the type of the variable as a TS. So let's define the type of my variable as a TS. And then now check the type. Now the type of the variable is TS. And now then plot it again. Now, if I just press the plot without even the type L, I have the right plot for the time series. So these are the differences between making plots for the time series. So let's look at all of the three variables and the time series behavior of these three variables for my example: cardiovascular mortality, temperature, and particulates. So you can see that the middle graph is different from the others. The only thing that I changed in the command is the type, which I just considered as a type as an odd. So now it connected the points. It shows also the points and the lines. There are a bunch of functions that you can make plots. So these plots, this command just make all the plots together on one plot. Sometimes if you are interested to make this. Or if you remember, we talked about the ggplot before. And if you remember, we had a bunch of comments for making a ggplot. But if you just define your variable as a time series variable and use the autoplot comment, then you can make the plot with the ggplot pretty much easy. You can also make the ggplot for all three variables together. Or if I just here, instead of, I use the same comment as before, but just use the facets equal to true. Now I have them on the three different plots, again using ggplot. So now look at the why I choose these three variables. I looked at the pair plots of the variables and I found out there is a correlation between the mortality, temperature, and particulates. So I want to consider here the mortality, the cardiovascular mortality, as my response variable, my response time series data, and somehow use the temperature and particulates to forecast this cardiovascular mortality. So again, we have a bunch of comments and functions, different packages that we can make this pair plots, like pairs, or if you wanted to have the correlation values also, we can use the pair panels. And these pair panels, actually, if you look at the help of the pair panels, you can see that it has a bunch of parameters that you can change. You can change the type of the correlation based on the correlation type that you want, based on the data set. And so you can see that there is a correlation, negative correlation between temperature and cardiovascular mortality, and positive correlation between particulates and mortality. But again, be just careful that this correlation is just a linear correlation. Now, first thing in any time series analysis is just defining the time series if it is stationary or non-stationary. So what is the stationary time series? Stationary time series is a time series that statistical properties such as mean, variance, and the correlation is constant over time and should not be a function of the time. And the reason that in most of the statistical analysis, we need the stationary time series is they are basically easier to forecast and predict in the future because their behavior is somehow constant and doesn't depend on the time. But in reality, most of the data sets that we have are not stationary, so we need to do some transformation over our data set to make them stationary. Let's look at the example and how we can see if our time series is stationary. We have some tests that we can check this, the time series is stationary or non-stationary. I just skipped those, but by looking at the autocorrelation function, partial autocorrelation function, and cross-correlation function, we can get some idea of what type of, and usually for the stationary time series, we have we can assign one of the ARIMA models. So ARIMA models are basically the statistical method and statistical models that, for the time series analysis. So any time series data set that we have should basically assign, time series should be basically assigned to one of these models. So let's look at the autocorrelation function for the cardiovascular mortality. And okay, I run all of them together, it's fine. So the one on the top left is the autocorrelation function for the, let's make it bigger. I think if I press this, doesn't show it. Let's run them one by one. So this one shows the autocorrelation function for the cardiovascular mortality. And you can see that we have just some specific lags of it. We can, based on this function, we can increase the number of the lags to look at the more correlation between them. But it's obvious that we have a significant correlation between different lags. And that's why we say this time series is non-stationary, basically. But we can see that based on this partial autocorrelation function, it seems that based on the partial autocorrelation function, we have the autoregressive model of parameter 2 and autoregressive model, autoregressive 2, or we can look at by the cross-correlation function, we can look at the correlation between two different time series variables. So up to here, autocorrelation function and partial autocorrelation function are actually correlation between different lags of the same time series, but cross-correlation function is the correlation between two different time series. So we can also make all of this autocorrelation function and partial autocorrelation function actually on one graph and using just one comment. So on the top, we have just using the TS display command, we can generate all of these three plots together. So the top is just the time series that we have and the autocorrelation function and partial autocorrelation function. If you look at the autocorrelation function for the 200 lags, it's obvious that we have the seasonality here. We have the pattern that repeats in some constant sequence of the time, which is 52 here. It's 52 weeks of a year. But we can see that based on the partial autocorrelation function, we have the autoregressive of 2. We have just 2 significant lags. So basically, when we have the non-stationary time series, since the autocorrelation function has the seasonality, we can see that we have the non-stationary time series, so we can stationarize it by some transformation. Most of the common ones is just looking at the difference of the lags. So we can find the display for the differences of the different lags of our time series. Now we can see that this is the difference of the lags. So first observation, second observation minus the first one, third one minus the second one, and so on. And looking at the autocorrelation function and partial autocorrelation function for this case, but still we can see that there are so many significant lags here, specifically for the partial autocorrelation functions. So which means we have the correlation between lags. So if we have the seasonality at first, remember before doing any differences, we figured out we have the seasonality pattern. And it's obvious from our time series, we have the seasonality pattern in every 52 steps. So now let's look at the difference for the lags of the 52 and the difference after that for second observation minus the first one and so on. Now, if you look at this, we can see that our time series is more stationarized, more random. We have the more random behavior for the seasonally and lag difference time series. And it's obvious from the autocorrelation function and partial autocorrelation function, there is a correlation at the lag of 52. Almost at the lag of 52, we have the significant correlation, which shows the seasonality. So based on this autocorrelation function and partial autocorrelation function, basically we recognize the type of the ARIMA model that we have. But you can see that it's hard to recognize all of this just by looking at the graph, and there's a high possibility of chance of making any mistake. So we can make this, find the best ARIMA model using the auto-ARIMA function. So by using the auto-ARIMA function, this auto-ARIMA function tells us what is the best possible ARIMA model fitting to this data set. And that's gonna help us to forecast the time series in the future. So this one actually tells us the result of this. When we run this auto-ARIMA function, we can see that the suggested ARIMA is ARIMA 211. And the next step for the time series is looking at the anomaly detection for the time series. So the detection of the anomalies for the time series is different from the regular data set that we have. So if we just looking at the TS outliers function from the forecast package, we can find the possible outliers. So the rest of the comments are just to generate this plot. But just by running this function, you can see that. Let me run this one. And then if I go to the console, and then just type this, then we can see that as a result of that comment, we have the indexes of the possible outliers and the suggested replacement for them. These are actually the indexes for these red points on the plot. Just indexes for these 2 points. And the other method that usually help us to analyze the seasonal time series is to decompose the time series to the trend, seasonality, and remainders. So we can decompose the time series using the decompose function and find the trend of the time series, the seasonality, and random, or sometimes they call it remainders. And we expected the remainders should be randomly behaved and randomly distributed. We can also regenerate this decompose using the STL function. I prefer using the STL function because the STL function has also more parameters to change, and more you can change different type of the parameters in this function and find the additive, multiplicative of decomposed time series. Okay, using this smoothing of mortality using the R function of Lewis, let's look at what this function is doing. Sorry. Okay. So here, on the same plot, just by using the Lewis function, Lewis comment, we can find the mortality cycle. So this comment actually just give us this blue line, the cycles, and the second comment give us the linear trend of our time series. So sometimes, for example, for the degradation of the power plants, if we are just interested in the degradation rate, then this trend is going to be more helpful. Or finding the smooth seasonality. We can also use the Lewis for the for finding the nonlinear relationship between two different variables. Let's look at this comment and see how we can find that. For example, here, if you look at the relationship between the cardiovascular mortality and the temperature, we can see that come on. So we can see that if you wanted to find the spline regression model, not just the linear one, this is going to explain the relationship between the temperature and mortality much, much better than the linear regression model. And we can see that the mortality increases at the extreme temperature. In the low temperature and the high temperature, we have the high mortality. So it's not just, also, if you remember, we had the negative linear association between the temperature and mortality, but that's, we can find the nonlinear relationship between the temperature and mortality also based on this function. And the last step is just using which is actually the main reason of doing the analysis of the time series is to forecast the time series in the future, forecast the behavior in the future. So let's look at how we can forecast it by using the ARIMA model. Using the ARIMA model, we can find the auto ARIMA model, fit it, and then just plot it. So this plot just gives us the mean average in the future and the confidence interval of the predicted values in the future. We can also predict it based on the Holt-Winters method. So if you are interested to see this methods, you can just go through those two textbooks that I had in my references. And I also added the PDF files of the textbook. So this is also, again, another forecast based on the Holt-Winter. But the last thing I'm going to show today is just a function that I wrote it based on the diffusion index method. And I'm not going to go through the details of this function, but if you just run that function and use the forecast, Is it running or? Okay, here. So now you can see that we have the more accurate result of forecasting in the future, not just the mean value and the confidence interval. And these are the references I talked about. At the end. So these are the two references for the time series analysis and the multivariate time series analysis.
All right. Hi, I'm Justin. I will talk through the second portion for the last 20 minutes. And so we'll be looking at various types of modeling for your data. So taking explanatory variables and looking at how you can use your models for prediction and for trying to gain insights into the types of data that you're trying to study. So links that I'll be looking at. And so, there'll be ISLR, Introduction to Statistical Learning. It's free. If you go to this link, you can get a PDF of it. It's here. Also, Open Intro Statistics. You can get a free version of that online as well. Great books. Both of them come with extras like labs and stuff with free code online. And just one other note that I will be including in the repo, it's already in the repo, is I took all of the labs from the whole ISLR book, took the code and then annotated all of the labs. So if you want to learn about, I'll talk about linear regression and multiple regression today and some support vector regression as well. But if you want to learn about cross-validation or subsetting, looking at PCR, looking at PCA down below, nonlinear modeling, so using GAMs and splines, decision trees, random forests, so all these sort of higher order models. Let's say we go to decision trees. All the code is here for walking through examples of how you do prediction using decision trees, as well as support vector machines and all this higher order machine learning algorithms. So really nice walkthrough there if you guys wanted to use it, as well as clustering, some sort of unsupervised machine learning. So these are sort of the links I'll be using today from Open Intro Stats, as well as some online tutorials for SVM. So we'll go back to R. We're going to check really quickly. Okay, cool. Okay, good. Okay, so let's start with linear regression, and you can see we'll go through linear regression, multiple linear regression, interaction terms, so not just your individual multiple regression terms additively, but looking at interaction between different variables, nonlinear transformations, so taking your data, doing log transforms, polynomial transforms of your data, and then fitting those. So if you want to use linear regression, but your data has maybe a quadratic curvature to it, and we're going to look at how we analyze the fits, and maybe your original fit isn't linear, but you want to convert the data to being linear, you can do a transformation and then use a standard regression fit. So we'll go through there. So correlation is probably the simplest way to look at a linear relationship. It's simply the strength of that linear relationship. So the more linear your data is, the stronger the correlation is, and between -1 to 1, negative being whereas your X variable increases, your Y variable will decrease, and positive correlation being both variables will increase together, trending together. So evaluating a model will take the residuals, so taking the distance away from your fitted model that your actual data is, and trying to minimize that using either the sum of squares or the sum of the absolute value of those errors, which is the absolute error. Those are your two standard types. So one here, let's go back to the PDF or the HTML. So looking at minimizing your error. Here's the absolute value of those errors, distance away of your data from the model, as well as the sum of squares, the sum of those residuals. That's most commonly used way is using least squares. It's easy to compute by hand and also is more computationally efficient. So if we're looking at conditions of a least squared regression, you want to look for linearity. So making sure this is for validating your model, diagnostics of your model. We'll look for linearity. You can use just a simple scatter plot for that. Nearly normal residuals, making sure your residuals have a nice distribution. You can use a normal QQ plot, which I'll show below. A constant variability, so the homoscedasticity of your data. So looking at the variability of your residuals about a constant 0, meaning there is no residuals and you have a perfect fit. And then a note with this is after you have your model, being aware of extrapolation. So, in this case, your data was predicting, you trained your data in a region where your high school graduation is, 78% and 95% or something. But if you were to predict that back to where you had 0 high school graduation in your state, well, there's no states that have 0% high school graduation. And if you were to predict with this model, you're going to have some sort of erroneous result. So obviously in this case, you can foresee there's no states with 0% high school graduation. But let's say this was just off of populations or sample sets. The only way that could be the case is maybe you had a group of toddlers have their own little I don't know, a state somewhere where they have 68% poverty and they're somehow able to get the other 32% to work hard. So, so just watch out for extrapolation whenever you do fit these models. So we'll go back to the code and start running it. So we'll run this first stage here. So if you look here, this first one will fail. Make sure this is large. And that's because we've loaded the data, but we actually haven't declared what these variables are. So if we get rid of this here and we go down to the next state, we'll see that if we set data equal to Boston, which is the set that we loaded from this library, we'll then be able to get a nice model. Additionally, as opposed to setting data equal to Boston, which is the data set, you can attach it. I would probably recommend not using this in a large-scale data analysis, but in this case, it allows it to stay inside the environment. A simple correlation, so you can see we have a negative correlation about 0.74, and if we plot the data, we see that seems about reasonable. We'll again generate that model, and then use AB-line, the function, to just use the model itself and overlay it over our data. So because it's our markdown, we have to run the whole chunk again. And there we see our linear model. And there we go, we can see the fit. This is the intercept, your beta value, and here your beta naught, and then here being your beta 1, which would be your slope. So from this fit, what kind of interesting stuff can we get from it? Well, you have your summary here, looking at your residuals, coefficients, look at your p-values, nice significant p-values, adjusted R-squared, 0.54. So all these standard model parameters you can get directly from the summary. But let's say you wanted to grab particular, you don't want to grab the whole summary, but you want to grab particular variables. Well, these are the options that you have. So coefficients, residuals, ranking, things like that. So if we pull, let's say, use coefficients, see the coefficients of the model, and confidence interval, 95, in this case, a 95% confidence interval about your data. With this model, we can take and give it a data frame, LStat, which was, if we look above, the x variable, y tilde x. That's how we fit the model. So if we give it some x values, 5, 10, and 15, we use a particular interval. In this case, we'll use confidence, and the next one we use prediction, with the difference being prediction intervals account for both the uncertainty in knowing the value of the population mean plus the data scatter. So your prediction interval, as we'll see, is typically larger. Well, is always larger by definition. So there's your lower and upper bound of those intervals. And if you want more information, here's a link to explain the difference between those types of intervals. And here again, just overlaying the data. So we'll plot this here. So okay, so we want to do some diagnostics on this fit. We've just done the fit and it seems to be doing all right. How good is this fit and is this a valid model? So standard way of doing this is just taking your LM fit and plotting it, and it gives you these 4 diagnostic plots. One being the residuals versus the fitted, which shows if the residuals have nonlinear patterns. You have your QQ plot over here. That's looking at if your residuals are normally distributed. A scale location. This is looking at if your residuals are spread equally along the ranges of predictors that you've given. And then residuals versus leverage, looking at how your model fits outlier, or how many outliers are on in your model, and do those outliers actually have an effect on the model that you've made. A very nice resource here is this link, which goes through understanding these diagnostic plots and showing examples of what would be good or bad. So for something like residuals versus fitted plot, you're going to be looking for something like this, where you don't see very much variability of your residuals, or you see constant variability. You don't see too much of a shape to your residuals. Normal QQ, looking at, you don't see any like curvature or deviation from what would typically be a straight line, fit there. Scale location, again, looking at standardized residuals. So you want some sort of small fluctuation and your variability to be constant. So you don't want to have a trend. In this case, we do have a trend. And leverage statistics. In this case, this is the only one where the shape doesn't particularly matter. You're just looking at making sure that none of your data points fall with outside these dash lines, being Cook's distance, which is a metric for defining leverage. So in this case, we do have some high leverage points, which could skew your linear fit in this case. And again, just some more diagnostic plots. This one looking at residuals, this one here at the student test, and then here looking at leverage statistics. And if we wanted to find, in that case of the plots we just saw, what's the highest leverage point, which we can see is probably this one here, we can just use the which.max function, look at the hat values, which is the leverage function, the leverage points, and we see it's at 375, which makes sense with what we plotted here. So if we wanted to, and we found this to be a high leverage point, we can remove that point, refit the model, and see if we get higher, well, I guess lower, higher fitting model, higher adjusted R squared. Multiple linear regression. So looking at using multiple explanatory variables in predicting a particular response. Here, additive, you can just add it in with a plus sign. The plus sign is you're not actually adding the values, you're just taking and tagging on additional predictors. So we can run that quickly, get the same sort of analysis. If we use the dot, we can take your, in this case, MED-V, looking at that being the response, and the dot saying all other variables in that data frame will be your predictors. Very nice at looking at what values will be significant and which ones will not. In this case, we see age has a really high p-value, so maybe in this case we want to remove age from, so we can take all the extra variables, or all the extra predictors, and we subtract age, so it's just not going to be using age. We pull that one out. Do the same thing, and just another way of doing it using the update function. So it takes your original model and then just updates the parameters without age in this case. So let that run. Okay, so now looking at interaction terms, so not just taking and tagging along extra explanatory variables, but looking at the interaction between those variables, predicting that response. So if we just use a colon, as we see with this first comment, that just puts an interaction term between those two variables. However, if we use this star, I'm not going to, just a star in this case, it takes the interaction terms between those two values, as well as adding in the individual terms of LSTAT and age, just as we did before with the plus sign. looking at nonlinear transformation of the predictors. So in this case, let's say we wanted to add in second degree polynomial fits. We want to transform the data before doing that fit. We can add that in here. I won't discuss, well, if you want to do analysis of variance, you can use ANOVA to look at the difference between two of your fits. And then again, evaluate that model with the time. I won't go through that. If you can use the poly function if you want to do, let's say in this case, a fifth order polynomial or any degree polynomial. Let's say you want to do the logarithm of your data before you do a fit. You can just use the log function right in line with your x or your explanatory variable. And again, getting the same sorts of plots. Predictors in R, it actually generates dummy variables automatically for qualitative values. So in this case, we'll use the ISLR data set, view this data, and you can see that this Chev block column has good, medium, and bad being the qualitative values. Well, when R goes and makes this fit with all of the extra values, all of the extra variables, it's still included because it used a dummy variable. So, and if we looked at that ISLR labs that I talked about at the beginning, something like a logit function where you're looking at logistic regression or looking at trying to classify low order classification, that's really nice with qualitative variables in that case. So let's go through, we have 4 minutes left using support vector regression. So this is a tutorial you can see on here. I modified it a bit, but essentially that. So take some data here, some 1 through 20 for your x, y, just picking some random oscillating variable values, and then we can show a plot of it. Okay, some sort of curved, set of data. We can make a model between y and x, just as we did before, and then I'll run all the code together so you can see the overlay of just the linear fit. Okay, adjusted R squared for that fit. So yeah, high 0.938 adjust R squared, so pretty good. But let's take a look further here. So do a prediction of those values, which is taking that linear fit, predicting in this case, a set of x values 1 through 20 onto that model. Then you get these blue points. And so making a quick function that I won't explain, but just looking at the mean squared error, which is just a common way of evaluating the error. We'll run that function. We see that the prediction error of that model is about 5.7. Okay. So using the package E1071, just a package you use for machine learning, it means nothing. Well, it may mean something. Someone knows. Let me know. So we can just use simply, as we were using LM, we can just use SVM, support vector machine, and run this. Now we have a model that's been generated. We can predict in the same way as before, plot that data, the original data, and then apply points. Apply the points over. So this is a trained model using support vector regression. And so let's check the error of that. So using that RMSE function that I made above. Okay, we see that the error is reducing. So, it's definitely getting better, but let's try to tune this model a bit, see if we can get some better parameters for predicting. So this actually, that SVM function is, we have 1 minute left, so we'll go quick. That's called epsilon regression. We're trying to minimize the cost function. So if we just simply tune those results using the tune function, plot that up again. Okay, looking at the tuning parameters, we know we want to be in this area here. We have the lowest possible error. So let's look in that regime, that smaller regime, run it again with a smaller bound, right? Looking closer between 0 and 0.2. And we see we have a local minima somewhere around in here. But we don't have to do that by eye. We can just use best.model from the tune results and let it predict. So now we see our error has decreased down to 2.04. So a pretty nice model. And we'll overlay that. You can see the blue is the tuned model and red is the non-tuned model. So definitely predicting better. looks like we're out of time for today, but additional things is looking at a smoothing spline compared to this data, as well as support vector machines for classification, not just regression. So looking at trying to, looking at the difference between trying to differentiate between different clusters of data. So with that, I think I'll conclude. Does anyone have any questions? Last 1 minute question. Yep, Amit.
What is the cost function for SVM regression?
Yeah, so there's different types. This one here is called an epsilon regression. Is the standard default SVM like that's running whenever you hit that function here. If there's a link at the top of this section here, which will actually explain like what that epsilon value is, but it's essentially like how looking at like for each value you're adding in to the model, right? As you're trying to train, like what's its influences and its like its influence on the model and how much each individual point is influencing like your predicted fit, essentially. I think that's the simplest way of explaining it. But if this link here will actually show you pretty nicely the difference between those models. So.
In the autocorrelation functions, when we plot lab on the y-axis, it says 0 to 200. So it's actually checking